We're actually waiting for Peter Matheson. We're waiting because I think you're supposed to. You're no good sitting there. Look, you're supposed to.
I told you I hadn't seen the schedule. I'm sorry, I'm having a natter with Shannon there, who I haven't seen for a while. Apologies. Anyway, at least you weren't waiting for me. I was actually here. So, okay, so thank you very much. So I'm Peter Matheson. I'm the principal of the University of Edinburgh. For those of you that are not part of the University of Edinburgh, you're very welcome. David and I have spent a bit of time together this afternoon because he's been contributing to an event at the Royal Society of Edinburgh around the funding of tertiary education in Scotland, which is a topic which is occupying quite a bit of my time at the moment. So it's great that, as to coincide with that visit, the Foundation for Science and Technology is hosting an event here. So thank you very much to everybody that's taken part in the organisation thereof. I know there's a lot of hard work being done in bringing everybody together. I know nothing very much about supercomputing except what Mark Parsons has taught me in the last 2 or 3 years, the stuff that I need to know. He gives me some scripts that, when I'm going to be needing them. But I'm looking forward to the discussion, and so it's a very great pleasure to welcome David in particular and Gavin to Edinburgh for the Science and Technology meeting. So over to whoever's speaking first. Is it you, David? Yeah, thanks. Welcome, everybody.
Thank you, Peter. Thank you very much indeed for that sudden mystery appearance. Great. Look, so wearing my hat as chair of the Foundation for Science and Technology, I'm delighted that we are here up in Edinburgh. Thank you very much to the university for hosting our event here. It's always good to get out of London, and it's particularly exciting to be up here at Edinburgh, a great centre of British expertise in supercomputing. It's great to be here, and we're going to hear about what's happening in Edinburgh and part of the wider national debate about investing in supercomputing, which is, of course, a very hot topic with a bit of uncertainty about exactly what might be funded. I'm choosing my words very carefully. And with the spending review due out very soon. Of course, this is such a distinguished gathering. We wouldn't do anything as vulgar as to lobby for public expenditure just before the CSR, but we may be reminded in the course of the evening's proceedings just why this matters so much. Let us get going. We've got 3 speakers. We're going to hear first from Mark Wilkinson. And Mark, I remember from my time as Chancellor of the University of Leicester, where he's based as Professor of Astrophysics, but he's also National Director of the SDFC DiRAC-HPC facility. And then we will hear from 2 other speakers. At the end of each presentation, they'll come and sit down. And then after we've heard from all 3, we will then assemble as a panel, both for questions and comments from you and also from our participants online. And welcome to our online participants. Do go to Slido. You can see the code there. You go to Slido and start putting in your questions. We're also very happy to take online interventions as well. Anyway, let us start first of all with Mark Wilkinson from the University of Leicester. Over to you, Mark. Thank you.
So thank you for the introduction, and thank you for the invitation to speak here today. Very, very much looking forward to an interesting discussion. That's not my slide. This is my slide. The topic we're going to cover today is exascale computing for research and the implications of quantum computing, AI, and net zero. And as you'll have seen in the announcement of the event, it's about looking at, one of the questions we want to look at is how have things changed in terms of what we need from computing, given the net zero requirements, and particularly now AI and quantum computing. So in these opening statements, we're just going to give some thoughts about various aspects of that. So the large-scale computing is a key requirement now for, and it underpins research in pretty much every area. So that's scientific research. It's the same in industry, it's in academia, it's in government and the public sector. So everywhere large-scale computing is a key requirement. And it's actually, we should think of these large-scale computers as research instruments. So they're not just laptops, they're actually instruments that are carrying out and are essential for the research process. The challenge, of course, then is that research doesn't stay still. And so there's a constant process of changing what research we're doing, the questions we want to answer, and that means we have to refine the tools that we're using. And the tools include hardware and software. So there are many reasons why the research questions drive changes in the compute requirements. One is you might need increased resolution. You want to do calculations that you can already do, but do them with greater fidelity. You may actually need to include new processes in the discussion. So it may be that there's new physics, or in a social sciences problem, you may need to consider different types of actor. You may be coupling of different models, so taking models from at different scales. So on a weather model, you might be looking at small-scale effects and things to do with the ocean temperatures, as well as large-scale and effects, and you need to merge these different things together. And a key thing now is uncertainty quantification. What you want to come out at the end is actionable outcomes, so information that you can actually use to make decisions, and for that you have to have uncertainties associated with them. All of these things mean that you end up needing more computational resources. No matter how efficient you are, the bigger the question, you always end up requiring more compute. And so what I'll explain is how an outcome-driven, so focusing on what you want to get out of the system, co-design approach to defining the ecosystem we want to end up with, that can give you a balanced set of services, and it allows those services to evolve as the research environment evolves. And so one example of that is the Tursa GPU-based system, which is part of the DiRAC facility. So it's based here at Edinburgh. So it was designed for particle physics theory research, but actually when large language models suddenly became a thing, it turned out it was ideally suited to training large language models. And so that's a case where having an ecosystem of services means you can then use them as the research environment evolves. And actually the first LLM to be trained entirely on UK-based compute was trained on the Tursa system, which is at the ACF, the Advanced Computing Facility that EPCC run. So what are the components then of a productive ecosystem? So a key thing is people. You need people to design the systems, build the systems, run the systems, write the software, and do the research. And so people, the people aspect is often overlooked, but they are absolutely critical, and it's something that the UK has a great strength in. Software is obviously vital as well. It's software that allows researchers to make use of whatever resources there are available, and it determines how efficiently we can use the systems. Hardware obviously underpins all of it. If you don't have a computer, you can't use a computer. So we do have to have investment in all of these. The critical thing is data. So everything, the value of the outputs all comes down to the data. The data contains the information, the insights, and everything that comes out of the research process. And so that really has to be at the heart of how we think of the ecosystem. But all of these aspects do need investment, unfortunately. So I will be mentioning the question we were told not to mention. There is a need for investment. So what's large-scale computing useful for? So but this audience, you'll all be familiar. There are many different ways it can be used. It's essentially delivering research and innovation, but across industry, academia, and government. So every area, as I said, is able to make use of it. I've just given some examples on this slide, but this is by no means, we'll hear more examples in the next two talks. It's by no means comprehensive. But the ones I've got here are things like changing how we do prototyping of new things within engineering. So if you want to build a nuclear fusion plant, they're going to have to be built as simulations first, and then they will be built. There's not going to be another prototype before the systems are deployed. So that's a complete paradigm shift in how we will be doing design of systems in the future. Personalized medicine, so being able to run a simulation of an individual human. This isn't an AI-based thing. It's actually being able to run a simulation of an individual and say, how will this individual's body react to a particular medicine? That is still years away, but there's work being done. It requires exascale computing to do that kind of calculation. Fundamental science, so the DiRAC facility that I'm the director of supports research in particle physics, nuclear physics, astrophysics, and cosmology. And so in all of those areas, large-scale computing is absolutely essential. But now with AI coming on board, so you want to be able to run very large models, train very large models on new data in real time. So while an event is happening, whether that's a natural disaster, a social event, or an economic situation, you want to be able to feed in the new data, retrain the model, and get information that you can make decisions on, you can use to make decisions, and you need that in real time. And so you can test scenarios when you're in using large-scale computing. The other thing that can help in a government context is to be able to bring together all the relevant data from many different sources, whether it's simulation data, detector data, survey data, put it all together and train your models much more comprehensively. And again, that can be used to deliver concrete outcomes that can then be, decisions can be based on. And another use of computing in the context of AI is actually to generate data that can be used to train the models and help to make them more robust to the risks of the model training data being poisoned, either accidentally or deliberately. So that's large-scale computing, and so exascale is a key component of that. The complementary technologies, I've couch the AI and quantum in those terms, because these are things where it's part of the whole ecosystem of doing research. And again, large-scale computing supports all of these, but also these have their own independent use cases as well, obviously. So with AI, obviously it runs on large-scale computing. So the two, AI and computing, are not distinct. AI is something that uses large computing. Quantum computing, you still need large-scale classical computers to do the error corrections for quantum computers. And that actually, I've mentioned there about co-location of systems, that has implications for how we design the ecosystem around the UK, because if every quantum computer needs to have a large supercomputer beside it, we'd need to include that in the planning. Secure computing and urgent computing. So secure computing, particularly for government and industry, that is an increasingly important area, but it's also something that is now possible. You can take a system and use a software-defined approach to break it up into pieces so that you can have a government department and an industry partner and academic researchers all on the same system, each of them having different security levels in terms of accessing what data they're using or generating. And I've mentioned already the value of having urgent computing, being able to use systems and get useful information quickly. All of those opportunities that can be used in terms of how we can use computing, obviously there are also the corresponding threats. In the wrong hands, either from criminal activity or state-sponsored malicious actors, there are threats that we need to be aware of. The kind of summary of how I would think about it is everything that can be done now, the threat becomes much worse if it could be done 1,000 times more frequently or at 1,000 times the level of sophistication. And that's the kind of change from having, let's say, a criminal organization that can access a petaflop of compute versus a criminal organization that can access an exaflop. Now, an exaflop system is hard to hide, so criminals are probably limited and, in terms of how much they can get access to, but state-sponsored systems are certainly a risk. And what the UK needs is to be able to counter those threats. So that means having a serious computational ecosystem so that we can fight against them, because you can't mitigate those kind of threats. And I've listed some there, but they include things like having the development of deep fakes, so you get a video call from a colleague asking you a piece of information, and it's so realistic that you just, even if you're a spy, you trust that it's because it's come in on a secure link. And so they are becoming much more sophisticated, and now the whole criminal process is being run using AI. So given all of those benefits, requirements, different use cases, how can we actually take account of that in a way that actually delivers something concrete? So the this is what the co-design process that I mentioned earlier essentially starts from what the use cases are. So you need to engage with all the people who will use the services and work out what it is they're trying to do. So that's the output-driven part, and that involves that those use cases will come from government, industry, academia, or wherever. Then you look at those and say, well, what does that actually mean in terms of the things people are doing? What workflows are they actually going to need to run? And that leads to a technical case. So that gives you a high level, how many services you might need, what they should generally look like. Then you can take those and turn them into technical designs by working with the computing industry. And there's been some great successes of this in the UK. And so one example, again, since we're in Edinburgh, to emphasize the success of the Tursa system. So there was a 6-month co-design process in the deployment phase of that system, during which the performance doubled for the workflows that it was supporting. So that is doubling the return on investment. In this case, it was science output, but however you define the return, it was doubled. And that was through a combination of the researchers who were working on it, research software engineers from DiRAC, the technical team at the ACF in EPCC, and the technical team from Atos, who was the provider. All of them working together delivered huge benefits. So going via a co-design process can lead to increased outputs, however you define, whatever those outputs are that you're looking for. It also has a net zero benefit, because it does, if you're able to use the hardware more efficiently, it doesn't necessarily mean your carbon footprint goes down, but your carbon footprint per unit of output goes down. And so that's a good reason for taking a co-design approach as well. As I say, DiRAC isn't the only example of this. There's IRIS, Jasmine, Grid PP. There are many examples across the UK of this. There's a lot of expertise in how to do this. And And so the final slide, spoiler alert, you now know who's next. So what do we need to do? So I think we're in a very good position in terms of having all the groundwork in place. We have, we can move from a good starting point, but there's no way to get around the first bullet. We need investment. So we need to invest in an output-defined computing system. It needs to cover all of the stakeholders that I mentioned, so not just academia. It needs to include industry, public sector, and government. We are good in the UK at computing above the flops that we on paper have. We've got a really skilled community in the UK. We have very extensive training programs to produce more, to increase the size of that community. There has been support for software development through Excalibur, but that has now ended, and that needs to be continued. And we have world-leading SMEs who are able to do working in the software-defined space. So there's all the groundwork is there. But so if we have the investment, the risk is if we don't have the investment, a lot of this could disappear. And if it does, it's very hard to rebuild it again because of the loss of confidence. The final thing is just to say we also need to continue to collaborate internationally. So EPCC has been leading on that, and Hartree in terms of European and other countries. The key point is we've got to use the language of the AI action plan. We've got to be makers in this space, not just takers. If our only engagement with international partners is to say, can I use your computer because I don't have one, that's not a sustainable way forward. But I think right now, with sufficient investment, I think it's a really exciting opportunity, and we could do an awful lot in the next few years with the right with the right investment to go with it. So thank you.
Thank you very much, Mark, for your Treasury submission. Excellently done. Very good. Very, very persuasive. Very persuasive. So thank you. Let's go straight on to Catherine Royce, who has been director of the Hartree Centre since 2022, and before that was Chief Digital Officer at the British Geological Survey, where she was recognised for her novel approach to the innovation and commercialisation of geoscience. So over to you. Yeah. Thanks.
And the first thing I do is go the wrong way. So I'm from the Hartree Centre, and I thought that I should be very honest about what where I come from and what I do. So I'm not an academic, but I am an academic because I work in the public sector research institute world. And this is what we're trying to do in the Hartree Centre. So my 10 minutes is going to be focused very much around the adoption of these technologies by our SME community and where I see things from that lens. We've all seen diagrams like this before, right? And I think it's clear, and my colleague Mark, and I'm sure the other Mark in a minute are going to say the same thing, is that this is where research is now, absolutely here. Doesn't matter what discipline you're in, this is what is going to get your new discoveries. And it will be part of it. Even if you are still going to a lab and doing wet chemistry, you will have started in silica over there. And I think the other point I want to make is how fast we are moving into new paradigms. It isn't taking hundreds of years anymore. It's taking 20 years from the big data, which I thought we were going to see my career out with. And now we are moving into what I'd like to say is the fifth paradigm. From my perspective, this is what the future of compute looks like. I've nicked this diagram from colleagues at IBM, so if any of you know IBM and you might have seen something like this, I've made it prettier, obviously, but it's this bit I want you to focus on here, is that compute is not going to be just about bits, it's going to be about qubits, so quantum, and it's also more and more also going to be about neurons, about neuromorphics, computers behaving like the human brain behaves. Computing at the edge, that is going to be massively important, and you can see the developments now. So if we are going to look at where the next great discoveries are going to be, I would say it is going to be in the convergence of high-performance computing, AI and quantum computing. So we go back to the point the previous speaker made. These are all tools to do your research, to do your business applications, to do your R&D as an SME. To get early adoption, we are not going to be able to use one single technology. We are going to have to put them all together. So composable infrastructures are going to become more and more important because me in business, I don't care what HPC quantum computer my algorithm runs on. I just need it to run, and I need it to run efficiently. So we're going to get to a point where there's an awful lot of stuff going on behind the scenes to enable me to run my algorithm. And I want to choose what GPUs I use or what CPUs I use. And that's a lot easier to say than it is actually to do it. So if we're going to become an AI superpower, we're going to innovate globally and empower locally. I want to highlight that point because when you are looking at innovation with the SME groups, you cannot treat them all the same. Each region has its own flavour, its own character, has its own problems. Okay? So you have to be able to take national ideas and convert them into local initiatives, taking on the culture of that area and the problems that area has. Yes, there are still issues around adoption in terms of training, but I want to highlight this in terms of our SME community. I know the data's from 2022, but I don't think it will have changed that much in 2025. If you're an SME, you are not a big organisation. Most of them are tiny. If we look at this data, all small, 5,400 have under 49 employers. So you're not going to have big AI teams or big data science teams. You're not going to have people with their HPC in their back pocket. To do your discovery, you are going to be reliant on a collaboration with others, whether that's with the big hyperscalers or with other providers of HPC AI algorithms. So we have to understand there is a community out there, and because most of our businesses are small, we have to look at how we get that adoption, because there's no point doing masses of work in the universities and it's all fabulous. So if I'm an SME, what are my problems? And these are my problems. I can't get access to supercomputing, and that's why Hartree was put up, and David was helped us get started, was that we have R&D facilities for industry within the academic ecosystem, and that's really, really important that we do that we understand what the SMEs are doing. But also to take on all of this stuff, we have to understand the ethical and regulatory considerations. 9 times out of 10, someone will come to Hartree and say, we've got this great idea, we want to use quantum computing. And you go, why do you want to use quantum computing? Because I read about it in the Financial Times over the weekend. Great place to read, by the way, nothing. But quantum computing is not the answer to every problem. Often we get down to the data. Is your data in a format that can be usable? Usually it isn't. Do you have a data policy? Do you have data governance? How unbiased is your data for the decision making that you want to make? And then it is, do you need quantum? Could you not use machine learning? Could you use AI? So you need to come somewhere that's going to give you the honest truth, which means you need organizations. We all need to have a breadth of understanding across all emerging digital technologies so you can put them together and resolve the challenges. So my final point on this, because I have other points to make, is that you need public-private partnerships, in my belief, to do this, because it is not something the research community can do on its own, neither is it something that the private sector can do it on its own. We need to work together. And there are some fantastic programs out there. Innovate UK's Bridge AI program has done brilliant things for the sort of underachieving areas, sectors are in our industry sectors, such as certain aspects, creatives particularly. Hartree's worked with IBM for the last 5 years. Not that I'm talking about the fact that our fund is coming to an end at all. I'll talk later. But I also wanted to stop now and talk about, if you are an SME in the technology area and you want to bring something into the community, it's really hard to do. Where do you go to get your stuff benchmarked? Where do you go to be able to prove that your stuff, your chips, can work better than one of the big chip manufacturers, right? Where can you go? You need somewhere to go to be able to do that. And that's why having a research ecosystem for R&D that is not only for our academics, but also for our SMEs is incredibly important. We can work as researchers together with these organisations, with these startups, to enable them to achieve great things. So I just wanted you to really think about that, because we are not going to get a semiconductor industry or new types of technology if once you become a startup, you do not get access to any of this great compute that we've set up. The other thing I wanted to highlight, I mean, this is just work by us, but there are other flavours that are doing similar work. But actually, when you're talking about early adoption, it's really important. This is work we did with AstraZeneca. But the key point here is we are seeing improvements even when quantum computers are not enterprise ready quite yet. So we can still do great work and show great advantage and pull our industry communities ahead of the game. And that's really, really important for a vibrant UK PLC, if you like. A vibrant UK is to be able to do things like this. So the future, what do I see as the future? I think we are seeing the next generation of semiconductors. There are some fantastic low energy semiconductors being developed for AI around inference. And remember that from an industry perspective, you will train your large language model and then you'll be doing lots of inferences off it. So actually having low energy chips that can do the inference for you will be a real game changer. I think biocomputing and neuromorphics, keep that in your wider vision. I think that's coming along to something that we are going to want to do more of. Error-corrected quantum computing, it is coming. I can see that in probably 2030, around that time where we will start to have the next generation of quantum machines. Some of the leaders in quantum are, that's where their roadmaps are. And I mentioned composable infrastructure, a lot harder than it thinks. Imagine plug and play. It's easy to say, it's very, very difficult to do. So in summary, I would say compute is the bedrock of modern life. Research, everybody needs to be computer literate. Skills need to be in that point of view where everybody does education, are data literate and compute literate. It almost needs to be a standard part of our education system now. The next decade promises to be absolutely awe-inspiring. What we think we know, I started Hartree 3 years ago. I started at Hartree. Hartree was still in existence before me, but I was told, just to remind you, I'm not that old, just to say that everybody told me, back off quantum computing, Kate. They're going a bit mad on it in Hartree. It's not anything. 3 years later, we are doing leading edge work with companies where you can really see where that is going and the application to quantum computing. So this world is moving at a pace that is unbelievably fast. And being a geologist and coming from the British Geological Survey, where geology works in millennial time frames, was a bit of a shock for me. We will continue to contribute. One of the important things is having institutes like Hartree within the ecosystem. We're not there to do primary research, that's not our format, but we are there to work with our colleagues to help industry get the information that they need to understand where they go next. And I just wanted to say that the future of compute isn't just about the big machines, and I think Mark has said that, and I'm sure Mark number 2 will say the same thing. He's going to kill me now. But it's empowering people. Right? It's empowering people. It's that work together. Computers are not going to take away from thinking, by the way. You are still going to have to think about what you do. So that's what I would like to end on. And to say thank you very much for inviting me. I've thoroughly enjoyed myself.
Very good. Thank you, Catherine. Fascinating. And that was the vision of Hartree, to be a resource especially for SMEs, so that they could understand and keep up to speed with what's happening. And we're now going to hear from Mark Parsons, Professor here, of course, Director of EPCC, the Supercomputing Centre here. And he has worked heavily on secondment in the EPSRC as the Director of Research Computing. I'm very pleased that we're able to be here at your facility. Over to you, Mark.
Great. Thank you very much, David. So you'd be very disappointed if I wasn't going to talk about Exascale, and I am going to talk about Exascale. I think, and I am going to make a plea for certain things, which I hope David in his previous roles will understand. But I also want to say some more general things as well about supercomputing and where we are. I thought I'd start off, I brought a GPU with me, because many people don't really touch these things. So I'll start it off here, and you pass it around. That's the sort of GPU that's inside Frontier, the world's first exascale computer. And that would cost you something around $80,000. Obviously, that's a broken one.
Such a high trust environment.
Yeah. So I think we're at an interesting point in the UK at the moment. We have a surfeit of plans. Yeah. Lord Valance actually initiated that one. It's a very good report. It led to the Future Computer Review, linked to the Science and Technology Framework, which actually weirdly was sneaked out the same day of the Future Computer Review. I think it didn't get the standing that it really should have. We've had the AI Opportunities Action Plan, which led to the government response to the AI Opportunities Action Plan. And I believe there's another report coming soon as well. So really, my first plea would be, I think we've had enough plans. the other problem that we have, I think, is we've also had a timeline that's been far too long. It's interesting, I was in Japan 3 weeks ago at a post-Exascale meeting, and I talked to people, and everybody in many countries have had long periods to bring systems together. The last Japanese system took in total about 14 years. But a lot of that 14 years in Japan was designing a chip and building a system and then building the computer. We seem to spend far too long trying just to get to the point where somebody will spend some money. And if we could reduce that, we could really speed up the value and the importance of supercomputing in the UK. And Exascale's with us now. I have to say the Japanese didn't get to the Exascale, but they had a valiant attempt, and I think everybody would agree that Fugaku really was the precursor to the Exascale age. China is not playing the international game at the moment and haven't publicly admitted to their Exascale systems, but they do have them. They submit papers on them. They're spectacularly large, complex systems built with Chinese technology. The Sunway system has 41 million cores. Right? You have 4 cores in your laptop. The world's first Exascale supercomputer publicly was the Frontier system at Oak Ridge in 2022, which is an enormous achievement. You know, I don't think people really understood how difficult it was. Aurora followed with El Capitan most recently. Interestingly, all of this program, the chip that you should be passing around at the moment, that was funded in a program called Fast Forward about 12 years before Frontier came into being. And that was the American government giving money to Intel, AMD, and NVIDIA. And why would they do that? Those are big, rich companies, you might say. But the American government realizes that science can push the boundaries of computing forward, but it's also lucky that it's got companies that can commercialize and make lots of money for the American economy and tax receipts for the government. So yes, they probably spent $2 or $3 billion on that program, but NVIDIA is a $3 trillion company now. And I think sometimes in the UK we don't really understand that. You can see where we are in Europe, or the European Union. Pre-Exascale systems in Finland, Italy, and Spain. The Jupiter system in Germany will almost certainly be announced in June as having reached the Exascale, and the Alistair Cox system next year in France. They've also already funded in the last 2 years 13 AI factories. And in total, if you read the bottom there, they've now spent, or will have spent by 2027, 10 billion euros. Finland's new project, which they've just received 612 million euros for, is just kicking off. And UK GDP is 11 times that of Finland, right? We are not remotely playing the right game at the moment. We're just being left behind as a country. I'm trying not to sound whinging as best I can. So we are making a little bit of progress. What next for national supercomputing? So we've now got the Archer 2 extension continued until November 26. Until earlier this week, Archer 2 is going to end in November 25. We don't have any news on the Exascale project, but obviously we're sitting with bated breath for the spending review. But I've stopped calling it Exascale now. We're not going to have an Exascale system. We're going to have the next national supercomputer service, because we're in the post-Exascale age. The Exascale's been done. The next American systems in 28 and 29 will be 10, 15 exaflops. And we just need to accept that. And you know, as Kate said, technology is moving at incredible pace at the moment. The new GPUs that we're now getting private briefings on are incredibly complex devices, much more powerful than the ones that were even used to build Frontier 3 years ago. We now think we'll be able to get an exaflop with between 8,000 and 12,000 GPUs. And this is really interesting, right? Because it's both a much smaller system, but it gives us considerable challenges. The Exascale design that we were going to go with in 2024 had 6,000 server nodes and 24,000 GPUs. So if we go with the 8,000 node GPU designs, that sounds great. It should be cheaper. But remember, we've got 6,000 users today that use Archer 2. We could have 10,000 on the Exascale system over its lifetime. If you have fewer server nodes, you have more queues. You do less science. You may do it more quickly, but it's still going to be very overloaded. At the same time, the 8,000 servers will not have as much memory as Archer 2 does today. And you have to think about supercomputing on two axes. You've got the axis of speed to do compute, but also that of memory. So in truth, if we go for an exaflop, I'm going to be very, very happy, but I'll be sad because we won't be able to do such large problems as we can do today. But we will be able to do problems that need a lot of compute much more quickly. Problems that may be, as Mark said, intractable today without the compute. So all of this suggests to me that we should set our target at least 2 exaflops, but you know, we shall see.
We have suggested that.
Indeed. So, you know, the purpose of this meeting was, this event was to talk about exascale AI, quantum computing, and net zero. And I wanted to make a few points which, in fact, I think complement what Kate and Mark have said. So I view AI as an application of supercomputing. You know, for many, many years, actually, AI used quite modest amounts of compute. With these large language models and with generative AI, the way you train these models needs a vast amount of compute. And it may be that we're doing all this wrong. Or it may be that we are mimicking the human brain, the way it learns from age 1, age 2, etc. We just don't know. But you know, as we were discussing earlier on, the human brain uses about 25 watts. An exascale computer today uses 18 megawatts. Right? So there's something fundamental we don't know about how all of this works. But AI itself, I view as an application of supercomputing, an application of computing. And I don't think playing exascale or numerical supercomputing off against AI makes sense at all. It's the same thing. AI is an application of supercomputing. So I'm agreeing here very much to what Kate said about quantum computing. We do a lot of quantum computing in Edinburgh, particularly through our work with the National Quantum Computing Centre and the Quantum Software Lab that Elam Kashefi leads here. In order to get to the point where quantum can be delivered commercially, we have to explore how we program these devices, what sort of algorithms they could solve, and what languages we need to program them. And that means that we've got to pretend we've already built the next generation of quantum computers and simulate them on supercomputers. And that's happening today. There's a huge amount of quantum simulation going on. And supercomputing is without doubt going to be critical to delivering the commercial application of quantum computing over the next 5 to 10 years. And then the other point was net zero. And I'm going to upset Gavin now by telling him that Archer 2 is operationally net zero already. And Peter's favourite story is that we do have plans to make exascale better than net zero by reusing all the heat, by heating the mine water under the data centre. The heat will flow towards built-up areas in Edinburgh, and people take the heat back out with heat pumps. And we've just drilled our first hole, and I have to say, I'm never drilling another hole. We wanted to do 3, we ended up with 1, but we did get to where we wanted to be. And maybe we should take some advice off a geologist. I'll speed up a little bit. So I want to give one example of a project, and this is the project I've led along with Lee Lapworth at Rolls-Royce. It was a prosperity partnership from EPSSC, a great model of industry academic collaboration. It allows you to work down at TRL 1 to 3, but solving problems that are of real value to companies. And what we focused on was the world's first very high fidelity simulation of a gas turbine engine in operation. We're doing the structure, the thermodynamics, the fluid dynamics, and the actual electromagnetics associated with that. And we wanted to move to 1 trillion degrees of freedom. We do regularly 10 to 100 million degrees of freedom. Today, we want to get much higher than that. And so the only way to run models of this nature will be on an exascale computer. And you know, in the classic style, it's a great collaboration between multiple universities, some SMEs, and Rolls-Royce. And just to give you an idea of why Rolls-Royce want this and why it's important and difficult, the aerospace engine industry wants to move to the point where engines can be virtually certified, so you can model it and get a certification. And this is what happened in the automotive industry 10, 15 years ago. But it took 10 years for the aviation industry to get approval from the Federal Aviation Authority to model bird strikes of engines and not have to do that physical test. In the 2025 to 2030 time frame, Rolls-Royce want to get to the point where they can do whole engine vertical certification. And that means we need to do extremely high resolution multi-physics models, as I said, and move from 100 million cells to trillions. And this picture on the right here actually is right at the leading edge of what is possible today. This is the next generation of commercial jet engine from Rolls-Royce. It's called the Ultrafan. And what this model is showing is, if you've ever been in a plane, Heathrow runway, very, very wet, you'll see as you accelerate on full thrust, it can hoover up a stream of water from the runway into the engine. And it's an extremely difficult engineering problem and modeling problem. And the work we did in Asimov is being already used in production use to model this. This is using Asimov work for the main fan and the airflow into the first compressor. But we're not modeling the compressor, we're not modeling the second compressor or the turbines, etc. Right? And we want to do all of it in the end. It's the sort of modeling that we should be doing in a complex way, because by doing this we'll push the whole area of aviation, hopefully in the future net zero aviation, forward. So 3 final points. What should we be doing? We should be bold. Right? We're post-exascale. The UK should aim, I think, for at least 2 exaflops, without a doubt. Our American friends are going to go, I think, for 10 exaflops in the next few years. We should plan. So we should be planning now for 2035. Right? It's easy to make an irrefutable case for doing this. We're just really bad as a community about gathering the evidence in order to make the case to Treasury. And given the time it's taken us to get to exascale, or hopefully exascale, we need to start immediately on the next system, because that next system needs to be bought in 2030, right? And I sometimes think we suffer enormously from the parliamentary term being 5 years. And then finally, I want us to compete again. I want us to push the boundaries of modeling, of AI, of quantum simulation. I want us to do missions again, or grand challenges as they called them at the start of my career, so that we can properly compete on the world stage, because we have some of the best computational scientists in the UK, and frankly, over the last decade, they've been let down by the research councils and the various governments. Thank you very much.
Why don't you sit there, Mark? Kate, you sit here. Other Mark there. Great. Good. Well, those were 3 fascinating presentations, which I'm sure will be reaching the Treasury even as we speak. So now there's an opportunity for you to put some questions, and we will also, through Gavin's laptop, we'll also be getting questions from our online participants on Slido. But now, who here would, first of all, physical people here in this room, who wants to put a question on any aspect of this? Yeah, let's start, Peter.
So I'm Peter Matheson, the principal earlier on. Kim Graham, who's the provost, who sit in front of me here. Kim and I deal all the time with our colleagues who understand information technology in a way that neither Kim nor I really does. And there always seems to be something more glitzy available at a higher price, and it would be able to do so much more if only we could just do that. And we hear this kind of a lot. How do we avoid that kind of, giving that kind of impression to those parts of government that don't really understand the role of supercomputing? How do we avoid giving the impression that we're just never satisfied? We always want the next glitzy tool.
Right, let's start at this end, Mark. That Mark, and then we work across. No, I think we got these. I think these microphones are working. Yeah. I think we're on. Yeah.
Okay. So I would say if we focus on what we're trying to do with the systems rather than talking about the glitzy thing, let the glitzy thing be, we want to be able to deliver personalized medicine or nuclear fusion or net zero aviation. And if we do that, these are the tools you need to do that. And so we'll always be, as we've all basically said, we'll always need more compute in the future. But as long as we're buying the most efficient, best for what we're trying to do, the focus shouldn't be on the actual hardware, because the interesting thing is what comes out. So I would keep it focused on that, because then you can decide, then it's up to whoever we're speaking to decide, is the thing that we want to do with it worth doing? And that, we'll argue that it is, but that's a decision for the country.
Right, very good. Okay.
I'm going to agree wholeheartedly with Mark, because I come from, and I'm not a computer scientist, I've come through a circuitous route into the world I'm in now. And really, we need to forget computer science and say, this is a problem we want to solve, and these are the people we need to solve it. And we have some domain specialists in that problem. So if you're doing personalised medicine, you've got your clinicians, your medical, your biochemists, sorry, I've got geology on my head now, alongside your computer experts. And it is only then that you can solve those problems. I remember bringing in data science and AI into the Geological Survey, and the key thing was to bring in specialists in those areas alongside the geoscience specialist, not ask geoscientists to suddenly become the best statisticians in the world, or ask a statistician to become a geoscientist. That's very different mindsets, and that goes back to that point. Don't think about compute, think of it as a tool, in the same way as you provide labs for people to use.
Yeah.
I thought Peter was going to say he spends his whole life dealing with difficult professors.
That as well.
So I think I agree with both of you, but I also think that there's a role for, and Peter didn't put me up to this actually, it's very nicely done, but I think there's a role to do difficult and different things. So this, I was going to show it earlier, but I didn't. This is the world's largest silicon chip. So this chip, if you have 4 cores in your laptop, this has got 800,000 cores. And it's just built for AI. It's from a Californian company. I've bought 4 of them for Edinburgh. But I think there's a role in our world for experimenting. That's why you're doing quantum, for example. That's why DiRAC's tried multiple different things over the years. So I do think there's a need for, I won't pass it around, but come and have a look at it at the end. It's very pretty. This one is broken because it's $1.5 million, and it's quite a lot. But I think there's definitely a need for us to show leadership in exploring new technologies as well.
Yeah, I would, looking at it from the point of view of the political process, I would say that a lot of smart but lay people who turn up as a special advisor or sitting in number 10 or even a new minister, when presented with these requests over the years, their first response is, why can't we just get it off Amazon Web Services? And you need, and I've observed, including the 2 Marks, you spend 6 months educating them why a physical exascale computer is needed, and you can't just get it off Amazon. So that is that issue, just for me, thinking back to my time, for example, the UKRI board. That's the first thing that takes time. And when you have regular changes and endless injections of smart people, some of whom have come over from the West Coast and are seen as gurus, they always ask that question, and it's held it up. And I would say, secondly, and this is where the doctrine has shifted, there used to be a view that the kind of AI requirements and the supercompute requirement for very large calculations were different. And so we had a bit of a debate about exactly what should be procured. And there is, thirdly, just the paralysis. When things are moving so fast, the moment you kind of almost literally sign the check, and it's going to take you 2 years to get stuff, by the time you get it, it's going to be out of date. So there's the sheer speed is an inhibition. So trying to account for why this process has been so laborious in the UK, I think those have also been elements. Yes, do.
So I think what you said about things move very quickly and that can lead to paralysis, but actually that's where the long-term plan, as Mark was saying, is so important. If you know where you're trying to get to, that, again, all the innovations, we should be looking at the latest shiny thing, not to buy a whole lot of it, but to make sure that that new shiny thing that Mark was holding, that may be the way to make AI more cost effective. And so we've got to be exploring those things, but you're always at the mercy of just buying the shiny things if you don't have a long-term plan. But if you know your goal is to deliver certain things on a certain timescale, like particular missions, let's say fusion on a particular timescale, you know what you're trying to achieve. So you're not just randomly buying shiny things. You're saying, this is the problem we want to solve. That is one of the things that might solve it. So you absolutely need an R&D program that's supporting that.
Yes. Yeah, and we got Hartree partly on the argument, absolutely, and Rolls-Royce is a great example. We had these leading companies that were clearly using these type of capacities, but their argument to us was that we haven't got a supply chain of SMEs that we can work with because the SMEs don't know how to use these technologies. And I set up Hartree on the idea, and it was wonderful just to hear from Kate, this is, and in her presentation, which was to ensure that supply chains behind primes such as Rolls-Royce or Unilever were also capable of using. And that when you've got a proposition like this that a lay person and a minister can understand, you can make more progress. Now, let's get another question. Yes. Oh, yes. Let's. There's a couple over there. So why don't we? Yeah.
Thank you. So Adrian Jackson from EPCC. When I first started in computational science in the early 2000s, late 90s, the UK was actually pretty world leading at this. So you could put on the floor computers that got into the top 10 in the world quite routinely. And that was even in a time when actually if you did wait for 2 years, you would get twice as quick a computer. So you could imagine that sort of delay mentality could have been there. I just wonder why the panel thinks we've fallen behind in this regard.
Yeah, and let's take also the question from the gentleman behind you.
I think I'm loud enough.
No, give the people online.
Sorry. Apologies. I'll put my civil servant hat aside and put on the scientist hat. One thing I'm trying to understand is how can we compel companies of Google and Microsoft and Apple, whose annual revenues are in billions, to really understand how they can be part of this venture in public-private investment. As this, I'm sorry, the pressures of budget in terms of when you are you're in the government and you're been advising ministers and all this sort of, it is compelling for us not to take the risk to that extent, right? So there are certain countries that have done better. But what else could we do in this country so that we can convince them to make a long-term investment, that sort of a thing? And I don't know what to do, but there's one thing I just want to compliment, is that there isn't a shortage of people who do not understand technology in the government. They do. I mean, as a matter of fact, STEM graduates in the civil service have increased up. Yep. But the pressure of the money means that you always have to make this difficult choice, right? And now we are talking about public-private. I come from Germany, where I worked a significant amount of time. Germans are willing to put it on the table as long as the government is also willing to open its wallet, kind of thing. So what sort of model would you really like to really champion so that we can have a supplementary funding coming from this cut of companies?
Two linked, now let's start at the other end with this part. There's two linked questions about just how our decision processes work and how we can do it better. Mark?
I think, sorry, I'm sneezing and crying at the same time. I didn't understand any of this actually until I went and worked inside the government. And I found it eye-opening. What I found was there's some really, really good people. I also found ridiculous processes, to be quite honest. And the processes that were designed to slow progress up, actually. And I think, in fact, did you not just write a report on this? You wrote a report about business cases.
I did, yeah.
Yes, I'll let you talk about that in a moment. Yeah, so I think there's that side of things. I do think that I found, one of the things I found most frustrating, when EuroHPC was being set up before Brexit, I was the technical advisor to the Sherpas, and I went backwards and forwards in the Eurostar to Brussels with the Sherpa, who's a civil servant. Unfortunately, that civil servant only stayed 6 months, and each one didn't have a science degree, they had a PPE. So I've educated about 4 of them in supercomputing. I didn't mind doing it, but I don't think it's a good way of setting science policy and representing Britain properly in these meetings. I think we do need to get better at that in the UK.
Okay.
So I'm in the process of writing a business case, and I'll just give you a reflection on it. So we got the new business case. It's been streamlined down to 15 pages of headings, which we have to keep to. and there are now 50 annexes related to the 15 pages to have enough information to pass through. There are 4 gateways you have to pass through. In government, there are similar number in UKRI, and it's taking 2 years, and I have to employ somebody to do it because it is so complicated to get through. So that is mind-blowing. But I want to get back to the point that you made around why these public-private partnerships. So I have a public-private partnership, very open with IBM. IBM get very nervous, and the relationship's working really well, and I think it's a very positive relationship, and I'd like to do more, and the next phase we'd like to have someone else coming in. The problem they have is cliff edge funding and no guarantee. So at the moment, quite fairly, nobody knows, well, no, that's wrong. There are some people who know what the spending review will come up with. Those of us on my side of the fence don't know. What I could do with knowing to help my private sector colleague is that there might be funding, there will be funding available. We don't know how much, we don't know what flavour, but there might be funding available. Because at the moment, I have to decrease all my industry pipelines down to 0 because I don't know that I've got funding next year. So I have to say goodbye to those pipelines and say, I'm sorry, but I can't guarantee that. We'll have to say goodbye to you. And IBM are getting more and more nervous because they don't see where that is. Now, everything could change overnight. But if you want to do long-term work with SMEs and private sector, we have to figure out how we deal with funding times that are tight. Because I am not going to say that it is not important on all the things that government has. And you know, we are in a ranked list, and we know that, and we understand that. But it might be something we could do.
Okay, we must have a word about business cases. They are not supposed to take that long now, and they are supposed to.
They do.
We will. Yeah.
We'll talk about that later.
We will. Mark.
Yeah. Thanks. So the 2 things I'd say. So I completely agree. The cliff edge funding is one thing, and I think again, in terms of the person who asked the question about this, you were talking about the government needs to open its purse as well. And that's it. It's a public-private partnership, and you're never quite sure if the public bit's coming. And so I think all of us benefited from the time that David was the science minister, because all of our projects were funded at that time. There was a big investment in computing, that was 2011 and 2012. Then there was a long period where there was nothing, and it just comes at random times. And so that's where the long-term plan, if there was a vision, if you look at Japan, they've got a vision that takes them out beyond 2030, and the exact envelope is not known because there are still various things that have to be signed off. But the fact that there will be funding over a 6-7 year period, that makes an enormous difference, and that there's a clear plan. And the other bit about leadership, I just want to, it's easy to keep on, we obviously need more investment in order to remain competitive, but the UK is doing very well. We haven't lost leadership yet. And so if you look at, it depends how you define things. So before Christmas, there was in my area, so in cosmology simulations, on Frontier, they did the largest ever cosmology simulation. So that was done on an exaflop machine, very impressive. There's more science coming out, and because there's more physics in the models that are run on the Durham system, which is orders of magnitude smaller. And so it depends, we are competing with the resources that we've got. We have, and that's all to do with how the systems are designed, how the people are using the software. Now, there's only so long that will work, and we're now at the point, in Mark's slide, it shows everybody else is now so far ahead that there's only so much you can compete. And now we're really at a point, I know it sounds like we're always saying, there's going to be a crisis tomorrow, but we are hitting a point where all the ingenuity hurts us. Yeah.
I would say, I think, just to add, first of all, that final point is really important. For a time, we got into the mindset that competing on the size of your computing system was incredibly vulgar. It was a brash race where people were just throwing massive amounts of resource at problems, and we were going to go for classy software and very smart simulations, and we weren't going to do this vulgar American Chinese rate for just throwing large amounts of energy to problem. And if you look historically at the strength of British science over several decades, that has often been what's distinctive about us. So that got us into a comforting sort of what now, and I think it got out of hand. I would say secondly, doing deals with companies is harder than it was, not just because of the public budget. There's more scrupulousness about exactly how you've conducted the procurement and where everybody's had a fair chance. And if a company comes to you with an idea, and it was IBM that first, the Hartree originally, it goes right back to conversations with IBM. I think to be fair to my successors, doing a deal with IBM now of the sort that I did when Hartree got started would be harder. People would say, but hang on, you've got to give Microsoft an opportunity, and to give Microsoft an opportunity, you've got to define exactly what you're after, and then you've got to put it out for public information, and then you've got to conduct a competitive tender. I think even in 10 years, that kind of model has become more of a requirement, and now perhaps we could look at reverting to more flexibility. So I think there are other factors as well. Now, we're going to collect an online question, because I haven't got my laptop with me. Gaffin, you've got give us a question from Slido.
Yeah, can I give you two? The first one, and it relates actually to what you were just saying, and Mark was just saying, how long until the UK has been left so far behind in terms of supercomputing power and skills that the damage done to science is irreversible? And the second question, what is the real difference in current predicted convergence of computational approaches compared to past convergence adoption issues? They feel very similar, is the comment written here.
John, the answer to the first question is the 11th of June, I think. That's the date of the CSR, isn't it? Anyway, so Mark, why don't you let me start with you. Yeah.
So remind me, the first question.
How long until the UK's been left so far behind?
Yeah. So for that, I would say the risk is if we don't have a clear vision of where we're going in the future, once we stop being able to retain the people that we've got and we stop attracting new people, that's when that'll happen. And I think the other thing, because I was actually discussing exactly this yesterday at a dinner in Durham, and the question of, what's going to happen next. So at the moment, as I said, the big systems are still running codes that don't have as much physics as is running on the UK systems. By next year, those codes will have that physics in it, plus they'll have larger systems. So, by next year, cosmology becomes much more difficult to compete. So we're not far off, unfortunately, and particularly at the moment with this cliff edge of all the services that we're talking about that are running now only have another 18 months, 2 years to go, and then there's nothing. And so if we have nothing, I'm assuming that the spending review will be more positive than that. But if there's nothing, then we have a serious problem, because that's at the point when we've already got anecdotal evidence of people starting to leave. But why would you come here if there's no sign of anything happening for a long time?
I agree with Mark. I mean, we had a colleague over from the National Labs in America. I think he was from Lawrence Livermore, and he said, well, if you're not going to have an exaflop, well, you're not really going to be playing in this world anymore. And I was quite taken aback by that. I do think we have Isambard AI, so we have had some investment. There is some good stuff. We are able to compete at the moment, but I agree with you. I reckon 5 years' time, we will be really, really struggling. We will have pushed systems to the max, and then we'll be having to use Euro HPC facilities, El Capitan Frontier, etc.
Yeah. Mark, can I actually just follow up on what you just come with? The other question, which we haven't yet, the other angle we've not yet covered, is Brexit and losing our partnership in EU facilities, which actually also gave us a degree of discipline. We were obliged to participate in discussions with other European countries that were thinking about this, and whether the So to think of optimistic angles, is the increasing close relationship with the EU, do you see there are areas of exascale computing where you could envisage us working more closely with the EU now?
So I ran some of Europe's largest HPC industry projects before Brexit. And as we head towards Brexit, it became apparent they were going to be funded from Digital Europe. And even after joining Horizon Europe, the UK can't take part in them. And I handed them to my German friend, who's doing a good job of running them. But I felt all along that the UK could stay in some way involved in Euro HPC, and you know, many of us are involved in Euro HPC. I worked very hard behind the scenes, passing messages from the British government to Euro HPC and vice versa, because they didn't want to be seen to be talking to each other about how the UK could become a participating country. And that happened, I think, about 18 months, 2 years ago now, which is great. But we can only partly take part in Euro HPC. We can't host systems. So every time, you know, my life with Exascale would be much easier, because the UK government would have put up £400 million, the Commission would have put up 500 million euros, and we would have had our whole budget. Yep. I think it's really, really important that we all get back into the habit of bidding for European projects. Yep. You know, EPCC, about a third of our income used to be from Europe. It's tiny now, and we're just getting into a mode of rebidding. I do see lots of opportunity for collaboration. The Euro HPC people have always wanted to work with us. I think we're in a better position today. I think I've always felt that science is an excellent way of nations to collaborate, even when they don't agree with each other politically. And I think there are huge opportunities. The one thing I would say to the previous question as well is the science is still going to be done. It's just not going to be done in the UK. I mean, it's not done in the UK. That means our best and brightest are leaving. It's simple as that.
Okay, let's collect some more questions here. Yes, on the side here, the lady there, and then along at the back. Let's do two here.
Thank you. Mark, I'm going to pick up on the point you just made and talk about the broader environment for research and the factors that draw people into research and keep them there. And thinking about the US context, where it's clearly, and I'm having conversations with students every day about whether they should accept a job in the US or whether they should go elsewhere. There's an incredible opportunity, obviously, to take a form of leadership that has been abandoned on the US side for the moment. And yet, there is ambivalent messaging around the UK's appetite and hunger for stepping into that vacuum, into that void. Particularly when it comes to support, financial support for universities' business models, but even things like the statement today in Times Higher Education about, you know, the role of university teaching no longer being about delivering research-led insights to students, but rather letting AI be the thing that students get knowledge from, and then we just do professional and career development, right? How can we reconcile this apparent enthusiasm in UK government for AI and UK tech leadership and leadership and innovation with these other messages that seem actually to dissuade a lot of young researchers from thinking that the UK is a place that wants to support research leadership for the long haul. So if you could just speak to where is that ambivalence coming from, and how can we somehow seize this opportunity that is going to slip away, as you say, and it'll go elsewhere.
And then down the back there, yeah.
Okay, so I'm the aforementioned Lee Lapworth from Rolls-Royce. More observations than questions. So the results that Mark showed, yeah, that was a full revolution of a compressor in 6 hours.
Now, when we started Asimov, we couldn't even do that, and we estimated it would take 9 days. So that is hugely impactful on the business, and that then feeds through to our products and therefore economic benefits. One thing I want to say is our model of working with universities. We've had our first project with the Mark was in 1995. We had access to, I think we actually had access to HPCX, but we also had access to Hector and then Archer and then Archer 2. And our model throughout has been that we want to pay for the specialists, the computational scientists, but for the research, we want access to the machines, which we've had. So that model of access to the machines where we pay for the computational scientists. And over that period, we've probably spent 10 to 20 million pounds supporting computational science research in the UK, in the science base. And that's in our own time we've also spent. So that model is one that we're very proud of and we would like to see continue with Exascale. Then an observation on quantum computing. We're also active in quantum. You wouldn't be surprised by that, I'm sure. And our estimate is 2030, 2035 before any real industrial impact. So people ask me, why is Rolls-Royce doing quantum computing 10 years before there's a benefit? And the answer is simple, that a lot of the benefit from quantum computing will come from algorithms. I'm going to echo a point that Mark made. And a lot of that algorithm development can A, be done on a classical supercomputer, and B, will still be run on a classical supercomputer even when bits are offloaded to a quantum computer. So this is all about skills and building the skills base, and we need to sort of really reinforce the skills in both classical computational science and not separate them from quantum. A lot of the quantum algorithms are basically, as Mark said this, it's just linear algebra. It's quantum mechanics is matrix mechanics.
I'll start with Kate on these, because you also do business, have close business links at Hartree.
So I'd start with your question. So from my perspective, and I'm not from the university sector, so my view is that there are too many new things going on. DSIT is a newish department, amalgamated from many others, still not fully formed and has still got that storming phase. So if I want to talk to DSIT, one person about Hartree, I have to speak to the AI adoption team, I have to speak to the AI for Science team, because they don't speak. I then have to speak to the Quantum Office for Quantum. All of these people are highly intelligent and lovely, but they don't speak to the AI for Science or the AI for Adoption team. And then if I want to talk about compute, that's not any of their job, that's the compute team. So already I'm trying desperately from my position to talk to lots of different people. And then if I've got UKRI as well, I've got lots of different fabulous councils that I need to talk to, all of which are responsible for different things. And then there's UKRI and itself, and then we've got a new exec coming in, and we've got new chief execs every couple of years under running the councils. So there's a huge amount of churn in that area where it is very difficult to pull through anybody to be able to say, this is the direction I'm going to, and a newish government. So that's why I think at this time, I have never seen quite so much stuff happening but not happening at this point in time. So that would be my observation. I think if we're looking for business, if we're looking for private sector stuff, they need clarity, and they are not going to move and support us if they can't see clarity. I totally agree, Rolls-Royce with Platform as a Service, we do that with many of our other global corporates. And what is nice is being able to provide different types of support to different types of organisations. So, and I do think that it's really important when we are outward facing and working with industry that we provide a whole set of experts to work with them, because we can augment their own teams, and that gives a huge amount of added benefits to the academics and to the industry colleagues that we're working with.
Mark?
So just picking up on your point about leadership being kind of dropped and why we're not picking it up. I think there's another aspect to that which I've seen in various discussions recently, that and this again is where the UK So I can't answer the question where the ambivalence comes from, but another impact of it is that there are data sets that were funded significantly by the UK, but are hosted in the US, to which UK researchers have lost access in the last few months because of changes over there. That's something I think we need to be aware of, and especially as we go into an era of foundation models. So you were talking about AI being the only thing we teach people, but AI will be more of a part of how science is done. It already is, but that will grow. If we get to a point where we're using foundation models within the scientific method on a regular basis, but we don't have the capacity to develop our own, and we're always reliant on, let's say, the US, if they suddenly decide that the UK isn't a friend of theirs, we might lose access, and that is, it's different to the past where you can have disagreements or whatever, and so even though we all want to work together, the tool is not available, and if that's embedded in our research process, and then suddenly it's switched off, that leaves us in a very exposed position.
Tell us a bit more. You are saying that there's data sets that have been partly UK funded. Yeah. Just to flesh that out, give us a real example.
Yeah. It was in the bio area. I don't have the name of it, but it came up at a meeting. Was a specific one. It was part of. I'll have to think of the name. But it was basically one where it was during when a lot of people were made redundant in the US. The teams that were managing these databases were let go of, and so they could no longer be accessed from the UK. Now, right. At the time, they were working out what they could do, but again, they were joint US-UK projects. But
so this was an effect of the sudden redundancies in parts of the UK.
Right. Right. Okay. And so it's just a risk when if you're dependent on others for compute.
Okay. Yep. Well.
So, Shannon, your question is really about internationalism, isn't it? And it's about how we respond to things becoming more difficult. And I've been thinking a lot about it recently because how we respond to the US is interesting. I think it's absolutely clear that we must keep engaging with them. And the story I'll give you is, people will be shocked by this, but we were paid, EPC was paid by the European Commission to engage with Russia from 2012 to about 2018. And I did it, and we went regularly to Russia, and we worked really closely with two very famous institutes there. And it was wonderful. We were scientists collaborating, but we were aware that we were collaborating with people who, one worked in the nuclear weapons area, one worked in the nuclear reactors area. And after the invasion of Crimea, I spoke to George Robertson, whose daughter was at Edinburgh, and said, I'm very nervous about this. Should we keep collaborating? And I've always admired him. And he said, you must keep collaborating. Even in the Second World War, there was contact across Russia, the US, even immediately after the war with Germany, et cetera, et cetera. And science is an international language. And I think personally that we shouldn't stop engaging with America. We should try and point out gently, not rudely, because that'll just lead to us all being cut off, where the American government is making mistakes. And I have to say, I think the present government is actually doing quite a good job. But I think we are in a very, very, a situation I never expected to see in my lifetime, particularly with the USA.
Can I check with Gavin whether there's anything else coming on Slido that you'd like to put to us? Has Angela got the microphone? And I'm also at the same time going to collect the last set of interventions here. Yeah.
So partly mentioned, and I think Kate mentioned this, but where does the government's AI growth zone initiative intersect with the need for investment in compute, which has been highlighted?
And I'm going to collect a last couple of questions here. Yes, the gentleman there, and then diagonally at the back. Yep.
Hi. Sorry. I'm not a computing scientist myself, but I'm from the realm of physics. And I wonder if there's a problem here, not the tragedy of the commons from economics, but the tragedy of the complex in the sense of political decision making. The Institute of Physics did research about the difficulty that physics deep tech projects have in getting private investment because investors don't understand the technology. Therefore, they can't make their own assessment of how likely they are to see a return on that investment. Fusion energy was mentioned. We've been about 10 years away from fusion energy working for roughly about 40 years. Now, in the public sense, it's different, the attitude to risk. from private investment, but the currency, especially for long-term projects where you're not going to see the benefits immediately, is that ministers will have moved. So what you really need is ministers to get some credit for the boldness, as Mark said, for investing now in returns that will only be seen later. So essentially, do we need public support for the idea of being bold so that it becomes more difficult to have a budget where you decide suddenly to not proceed with an £800 million investment?
Right. And I think at the back there, yeah.
Thank you. Yeah, there we go. Hello, it's Oliver Brown from EPCC, and so we've already touched on this a little bit, but to a greater or lesser extent, everything on the title slide except net zero is export controlled. So my question is, what does the UK do if we are suddenly told that NVIDIA or AMD cannot sell to us any longer? Should we be doing more protectionism of our own industries in tech, effectively, to try and defend against no longer being able to purchase from our US allies?
Right, and I think there was, yes sir, we're going to squeeze in one quick comment here, and then I'm going to give our panelists the final word. We're going to go across the panel.
David Wallace, I helped to start EPCC. A bit of a dinosaur now. Any future with China?
So, let's start here. Let's pick up on, because your final comments were about internationalism. Yeah. So we've got some delicate issues about exactly what we can rely on from the US, what we should do with China. You might want to comment about that, and also the AI zone question as well.
Very complicated. So the two chips I've shown you, both made in Taiwan by TSMC. And even if America builds some of these fabs, they're not going to do the really small stuff. So I think we are entering we're really properly in the middle of the silicon age at the moment, actually. And it's become much more valuable than anybody thought. And it's actually changing the way the world operates at a fundamental level internationally. You know, some people might think this is the previous moments in time in my lifetime have been about oil, in fact. Actually, this time I think it's as much about silicon as it is about oil. Do I think we should work with China? Of course I do. Do I think we should call the Chinese government out when they're behaving badly? Of course I do as well. In the same way as we should call the American government out. In all cases, polite, we should still call them out. I think there's a lot of fear about China, and yet Chinese students come to this university and we have a wonderful time with them. I've got a huge number of students in my MSc who are from China. Right? So we shouldn't fear our Chinese students or friends or collaborators, but we should understand that their governments may not think the same way as us.
Right. Thank you. Kate?
So I'll tackle the AI growth zones because I know a little bit about that. So my understanding is compute in DCIT is different to AI growth zones. AI growth zones is about getting industry to pay for the hyperscalers to work in an area where we unlock planning and we encourage business growth, and it's around the planning and venture capital, and it's that side. And at the moment, the compute side is considered separate, although we have said sort of 20 times the power of what we've got now. What I would like to see is that moving together. I am not up to speed on where the conversation has gone, but I know a lot of conversations have been had with people like the local authority. So I was at Greater Manchester City Authority yesterday, who were saying, oh, well, we're talking to DCIT because we think we don't want one great big hyperscaler. We want to do lots of little things, and we think that would be better for our region. So there's obviously some really good conversations going on at the local level about what an AI growth zone could look like. So that's my sort of feedback on that.
Thank you very much. Mark?
So I'll talk about the AI growth zones and then the comment about ministers being brave. So on the AI growth zones, I think like Kate said, they're distinct from the compute side, but the compute side of those, I would hope, will be part of the same discussion, will be part of this ecosystem. As Mark said, AI, you can call it an application. It's not distinct from large-scale computing. It's something that we do, and it's the tool that you need. You need large-scale computing to do AI as a tool, and therefore, decoupling the two and saying this computer is only to be used for AI and we'll have another computer that's only to be used for something else, that doesn't make sense, because tomorrow it may well be that AI needs a different type of hardware. And so if there's a divergence or a change, right now LLMs are using GPUs and so are simulations, so it's converged, but it doesn't have to stay like that. And that may not, as Kate said, as the industry moves towards inference, you can do inference very efficiently on CPUs. So again, that could be driving in a completely different direction. So, but it needs to be part of a whole discussion. So the AI growth zone part is great to encourage, adoption of AI. The compute part of that, I think, needs to be part of this whole exascale wider discussion. And regarding the kind of rewarding bravery, I think, yeah, these investments do cost a lot of money. I think, as Mark said, we have to make a case that's really ambitious and that explains why it is that amount of money, and indeed in the that amount of carbon, is being invested in whatever the missions are. And I don't think that the ministers or people outside the particular research field don't need to understand the detail of the research. They don't need to understand the detail of how to build a particular type of computer. None of that matters. We can sell the vision of what we're going to do with it, and I think that's how we do it. But we've got to allow ministers to be able to take a risk, because, again, if we have a good ecosystem, lots of good things will come from that, and that there's no question of that. So if we're going in the right direction, then I think it's not a huge risk. Individual projects will fail because that's the nature of them, but that's again why you spread the risk around. But yeah, allowing them to make a big investment at the risk of it not delivering a particular headline I think is important.
Good. Well, thank you very much to our panel. I think in a way, and it's interesting how much of the Q&A has focused on decision taking and decision processes. And that, I think, in itself, in a way, tells us there is a problem. It's a pity that that's what people are preoccupied with, and there are some important lessons there. And I think the community has been incredibly tolerant of at least 5 years when essentially this procurement decision has been going round and round and being reviewed. And I think both Marks have been involved at least back to 2019. And it is not a happy story of the way in which decisions have kept on being postponed. I'm going to stick my neck out. I do not have inside information on the PESC round, and indeed the only thing I do know is the last time I was checking yesterday, there isn't even a final DCIT Treasury agreement. There are negotiations are still underway, but I think it is extremely likely that there will be something for this computing requirement. It is so clear, this is a government that does attach a lot of weight to AI, and it's clear from the work of Matt Clifford and others that when you look at AI, we also need to invest in this type of compute capability. So I hope that this FST discussion is one of the last ones of a review process that has taken 5 or 6 years, and that we get, and it won't, and even if it is allowed for, I'm not sure you'll get the announcement on the 11th of June, but in the course of the following few months, people get a clear sense that this is now proceeding. If I were to try to end on an optimistic note, I would add it's interesting, as well as processing, as well as arguing about process and talking about computer processing, we had said relatively little about data, and the UK does have quite a precious national asset in high quality data that's not yet been scraped and is not yet out for the big systems, and there's a lively debate going on within government about what we can do with that type of data. For me, wearing my hat as chairing the Regulatory Innovation Office, I'm working with the Turing on whether we can take very well-defined data sets of the decisions and decision processes of regulators to create a usable guide for on how the regulatory process impacts specific sectors, distilled from published decisions and private decision processes. So and those are areas where the UK does have a national asset that is valuable. And we also do have, it's interesting, all the international exchanges. I agree with Mark, we do have to keep on talking to these people. And it is a nice lead-in to the next FST event, which will be on the 11th of June, back down in London, and is about science and research collaboration with Africa, which we think has got great potential where we should do more. But thank you very much for this evening. Thank you to our panelists. Thank you to the University of Edinburgh for hosting it at this wonderful facility. And I see some glasses of wine over there. And so now we should adjourn. Thank you very much indeed.